Now that we've learned the theory for the partial derivative, we're actually going to practice with some examples. So we have a function z here that's dependent upon two variables x and y. But when we look over here at x and y, they're each dependent upon their own set of variables. X is dependent upon r and s, and y is dependent upon r and t. So they'd like us to find the partial derivative of z with respect to s. Well, the only s in the game is right here, so we get to that through x, like that. So the partial derivative of z with respect to s would be, and actually I could have used ds there. Oh well, too late. That would be the partial derivative of z with respect to x times the partial derivative of x with respect to s. Okay, so we take the derivative of z with respect to x. That's a partial derivative. So you look back up at z, pretend that the y's are constants. So then the derivative would be y, take away 2, and then plus nothing because the derivative of 3y is 0, so because that's constant. All right, now what about the derivative of x with respect to s? So pretend that the r is constant here, it's just a number. And so the derivative of that would be derivative of cosine, which is negative sine. So this would be negative r sine of s. And there you have it. All right, now we could technically substitute what r is, or what y is into this. So you could say, oh, but that's r cosine of t, take away 1, or take away 2, sorry, take away 2 times negative r sine of s. That is also possible, and that would also work. So it's kind of, do you want to leave y in there as an intermediate variable, or do you want to eliminate your intermediate variables? So this leaves the intermediate, and the other one does not. The intermediate variables being, of course, x and y. And the answers, they're both correct. It's just kind of, you use whichever one's more convenient for you. All right, now what about the partial derivative of z with respect to r? Well, r has a couple more ways to get there. So it has two paths. So we're actually going to have to use both of them. So we'll have to take the derivative of z with respect to x times the derivative of x with respect to r. Then we'll have to add to it the derivative of z with respect to y times the derivative of y with respect to r. So we need two of them because there's two ways to get to r. R is here and here. All right, so let's start with this one. So derivative of z with respect to x, we already know that's y minus 2. So that's y, take away 2. Derivative of x with respect to r, well, that would mean that r is your variable and the cosine of s is constant, just some number. So a number times r, the derivative is the number. So it would be cosine of s plus, okay, now the derivative of z with respect to y, that's new. So that treats your x's as if they're constants. So derivative of 5y would be 5. So the derivative of xy would be x plus nothing plus 3. And then the derivative of y with respect to r would be cosine of t. Now this is perfectly fine. That is the partial derivative. That leaves the intermediate. If you want to eliminate your intermediate variable, intermediate, which in our case were x and y's, then you would substitute. Y was r cosine of t, take away 2, times the cosine of s, plus x was r cosine of s plus 3, times the cosine of t. I got a little lazy about my parentheses there, but just to make sure it's clear. So this is also perfectly fine. And again, we sometimes use one, we sometimes use the other. It just kind of depends on what we're trying to accomplish, but they're both perfectly valid. All right, so this one eliminates the intermediate. This one leaves the intermediate. And if you're wondering which one you should do, the answer is do whichever one you want. You always start off with the leaving intermediate one. And if you have to eliminate your intermediate variables, then you would just take that extra step. Okay, let's do another one. So w is equal to the square root of x squared plus y squared plus z squared. And of course, since I'm taking a derivative, we all know right away we need to get that square root out of there. So I'm going to make this into x squared plus y squared plus z squared to the half, just for my own benefit. And then I'm going to write a little diagram. I always do a diagram. So w is dependent on x, y, and z. So x here, y here, z here. Now x depends on a and c, y depends on b and c, and z depends on a, b, and c. Oh, Lord. And of course they want the derivative with respect to c, the one that shows up in all of them. So that's going to be fun. Let's start off with, I'm sorry, I'm just trying to grab a color here. All right, so I'm going to take the derivative of w with respect to x with respect to c. Let's start there. So the partial derivative of w with respect to c will be equal to the partial derivative of w with respect to x times the derivative of x with respect to c plus, now I need the middle one, so that's w to y to c. So the partial derivative of w with respect to y is the derivative of y with respect to c. And then one last one over on the right, w to z to c. So the partial derivative of w with respect to z times the derivative of z with respect to c. I'm obviously not going to be able to fit all of this into a horizontal line, so I'm just going to kind of work my way down here. Okay, so let's start with the wx thing. So that would be 1/2 times x squared plus y squared plus z squared to the negative 1/2 times the derivative of the inner part with respect to x. Okay, well that means that x is the only variable, and then these two things are just constant. So that would be 2x. Then I want the derivative of x with respect to c. So if I look at this right here, derivative of x with respect to c would be just a, because that's a constant times c. So that would be a. All right, that's that piece. Now I'll do the next piece. Derivative of w with respect to y would be 1/2 x squared plus y squared plus z squared to the negative 1/2, but now it's times 2y, and the derivative of y with respect to c would be 2, because you bring the 2 down, 2bc. Like that. Plus, last one. So it'll be 1/2 x squared plus y squared plus z squared to the negative 1/2 times 2z. And then I need the derivative of z with respect to c. But if c is the only variable, these are just numbers times c. And so the derivative of that would just be the numbers. So it would be a squared b squared. Now, if you're savvy, you'll notice a few things. For one, 1/2 and 2 cancel. Oh, I should do it in a different color. So those cancel, these cancel, these cancel. I mean, they divide, because 2 divided by 2 is 1. So those are all gone. And then you'll also see that there's this x squared plus y squared to the negative 1/2 in all three of these terms. So I'm going to start by factoring that out. It's x squared plus y squared plus z squared to the negative 1/2. Now what does that leave me up in the first term? If I take that away, I'm left with an x and an a. So ax plus, in this middle term, I'm left with a y, a 2, a b, and a c. So 2ybc plus, and then let's see, a z at a squared and a b squared. There you have it. I mean, it's not pretty, but it works. Right? Now, it definitely left the intermediate variables in there, and I don't even want to think about it, because if I try to get rid of the intermediate variables, I'd have ac squared. Well, I mean, I could try it here. A times ac plus 2 times bc squared times bc plus a squared b squared c times a squared b squared. There, I just redid them in colors to help you. So it's that a right there, becomes that A right there. And AC is what's standing in for your X. And then there's the 2 and the Y, and then there's the BC that was sitting there anyway. And then there's the Z, and there's the A squared B squared right from there. So this right here was Z. This right here was Y. Well, 2Y really. And this right here is X. And all of that needs to be divided by, if I want to get rid of all my intermediate variables, I'd have to make a square root of, and then instead of x squared, I'd have ac squared plus bc squared squared plus a squared b squared c squared, like that. If I want to try to simplify this just a touch, it'd be a squared c to b squared c cubed, and then I have an a to the fourth, a b to the fourth, and a c, all over the square root of, let's see, a squared c squared plus b squared c to the fourth plus a to the fourth, b to the fourth, c squared. There. That's not too bad. It's just a lot of a's and b's and c's. It's really easy, of course, to make little mistakes as you go. So just try to be very careful when you're substituting. But you'll notice you really can't do the entire problem at all unless you have this diagram built to build these chain rules, right? Then you use them. So again, this one leaves the intermediate variables. This one does not. The intermediate variables being the x, y, and z. And this one gets rid of all of them.